All right. Well, yeah, welcome to the Tech Forum presentation. Lauren and I will talk all about the what we are adding to trusted firmware to address some new cores coming out at a new architecture, in fact, coming out at ARM. So thank you for joining us. And yeah, in particular, okay, cool. And yeah, so we'll go over on the docket today. Basically, we'll tell you what we did and how we did it. and well, what we did, first of all, we'll start out by explaining what these new, we're calling them, in abbreviated form, we're calling them V8-R64 cores are all about. As you'll see, it's a new and much more powerful version of the R cores, that real-time oriented cores, and they're basically very similar with the A-type cores, but as you'll see, they have no EL3. They have some MPU functionality, and everything is secure. So we'll go over all the ramifications of those. And then we want to talk about what sorts of functionality we are putting into TFA to help support them and why. And then talk a little bit about the porting approach that we took and some suggestions, some ideas for how reviews could proceed with that toward the end.
Yeah, so getting into what is V8-R64. So yeah, as Gary mentioned, it's the next generation.
Just to clarify, technically, the technically accurate name is Armv8-A. Yeah, it's technically V8-R AArch64 architecture, but we're just abbreviating it as V8-R64. So anyway, just FYI. Sorry.
Yeah, looking it up, that's probably the name that you'll find. But yeah, so it's the next generation R class family, but it's AArch64 only as opposed to the previous R class. And Cortex R82 is the first implementation. These cores are especially targeted towards deterministic performance. So, for example, avoiding the unpredictable timing of table walks. Markets that have shown interest are automotive and computational storage. And for reasons like you'd expect, the R class community is excited about the vastly increased address space, much higher performance, and then the V8-R64 can now support rich OSs in addition to comparatively Spartan RTOSs. So this link has a little more info on that as well.
Yeah, just a comment here. As we'll see, previously on R cores, it's been very hard to do some, nice, lovely user interface type functionality with comparatively down to business, I guess you could say, RTOSs. But here they have now the ability to bring up, in addition to an RTOS, a more plush user interface type functionality. So that's got our people, the R core people, very interesting. Anyway, just sorry, wanted to inject that.
Yeah, so these are some of the main differences between V8-R64 and the A-class cores. So there's no EL3. So EL2 is essentially the EL max. Everything is secure. And for stage 2 translation, there's MPU support only. And then for stage 1 translation, it's a choice of MMU or MPU. And there's no AArch32 support. So here you can kind of see the comparison of what V8-R64 is as far as what ELs are supported as opposed to V8A. So you can see it's kind of a subset here and secure world only.
And so, as I mentioned, MPUs are supported in this. We'll talk a little bit more about MPUs, but this is a picture of, as you can see, it's V8A. This is what we're used to seeing. And just as a review, most people, I'm sure most people know this, but basically the concept is that you have stage 1, stage 2 translations. And this picture in the upper left portion is what the guest OSs each think is the whole world. They're Earth-centric, naive Earth-centric view of the world, and then the hypervisor and secure monitor together in their all-knowing sun-centric knowledge actually remap them around with stage 2 translation and pull a fast one on them, so to speak. But they think that this is their entire world, and then they actually remap with stage 2 translation. Anyway, yeah, you know that I'm just reviewing, because here's what happens when you go into the V8-R64 arena. First of all, you don't have EL3 as we mentioned, so that means you can't switch as Lauren mentioned. You can't switch between secure and non-secure that way. So you have to be one or the other, and so we call everything secure. Then the stage 2 translation is strictly MPU, only MPU, but the stage 1 translation could be MPU or MMU. So on a Linux type operating system, you would run that through an MMU, most likely. And then the RTOS most likely would run through an MPU, a stage 1 MPU, and then all of those are translated the second time through an MPU, strictly through an MPU, only MPU is available at that level.
Hey, so sorry, I had a quick couple of questions. Is that okay?
Sure.
Yeah, so a couple of things I'm seeing, right? So I haven't seen you address caches, because I saw you said MMU can cause jitter, but so can data caches and instruction caches, for example, right? So is there a reason you're avoiding it on the slides, or is that not considered?
Yeah, so a common way to address that, there's lots of ways of addressing that. I don't know what are the most common ways. Maybe Robin might want to say about that, but I know that a common way to that is to have on-chip SRAMs and put data, timing critical data into on-chip SRAMs. That's a common way to do that, and then lock it down, lock down the. Yeah, so yeah, that's a possibility. Do you have any thoughts on that, Robin?
Yeah, so it's pretty much along the lines of what you said, Gary, but basically a fundamental kind of philosophy with V8-R64 is that if you're running something with the optional VMSA, right, the bit that can allow you to run a rich operating system, for example, you are obviously going to use that for stuff that's not as time determinism sensitive as the stuff that you're running under the RTOS, right? So that's just one thing I wanted to call out. We will probably come back to this as the presentation progresses. To the more pointed question made by the gentleman, if you're running like the previous kind of generation of cores, right, Cortex R52, etc., where you did not have VMSA, you just had an RTOS using PMSA, so just MPUs and memory regions. The most kind of common design pattern is to rely on TCMs, tightly coupled memories, for code and data that needs close to single cycle penalties for access. And yes, if you want to use IND caches, then you have to kind of like do the due diligence in terms of making sure that your code and data is laid out in the address space in ways that doesn't cause cache-induced time non-determinism. Right? So the bottom line is over here with V8-R64, you're fundamentally just extending the previous style of doing stuff into this new architecture with a wider address space. And if you want to use a rich operating system like Linux, which you can, by the way, you shouldn't be using that for time determinism sensitive stuff in any case. if Linux has induced, like for example, it makes a reference that requires a page table walk in the MMUs, the Cortex R82 microarchitecture has support for ensuring that if an interrupt comes in for the RTOS, that interrupt is delivered in a fixed upper bound of time. Yeah. So
Okay.
I'm not
Okay,
sure
so-
whether that
And,
answers your question, but ask more and I'll try and make it more specific.
Yeah,
Yeah.
I think that does answer it. I was just wondering if there's something inherent in R64 that prevents IND caches, but it seems like that's not the case.
No, that's not the case.
Okay, and one other quick question, right? So what is, so typically for hypervisor, here it says it's only stage 2 MPU, right? But what is the equivalent of, TTBR0 EL2 on the R class? So how do I separate the hypervisor address space from, the guest address space?
So I'll have a crack at it, Gary and Lauren, you
Sure.
can jump in.
Feel free.
Basically, there's a stage 2 kind of MPU, right? So you have only PMSA at secure EL2 over here. What that means is that any of the addresses that are kind of the result of a page table walk from the rich operating system side or the result of a direct access made by the RTOS, they are further rationalized by the MPU at secure EL2. Okay, so that's one thing. Second thing, if you have your hypervisor and if you have your virtual machines kind of running underneath and at secure EL1, everything is basically flat mapped, right? So you'll have to kind of make sure that you are carefully selecting slices of your physical address space to keep things in line. Right? There's no translation, like second stage translation at all.
Yeah, the MPUs is important to remember. Do not translate addresses. They still call them translations, but well, some of the attributes can be changed, but everything is flat mapped when an MPU is involved. So.
Yeah, so the typical next question is then what exactly is the role of the hypervisor? And I think it's worth quickly calling out that as opposed to like classic kind of hypervisors which try and manage physical resources by doing effectively time division multiplexing of those resources across multiple operating system contexts, right? The intended model over here is one of a static partitioning hypervisor, where in the fast paths, the hypervisor isn't actually intervening for the large part. It only intervenes if someone does an out-of-bound access. So it's really a partitioning model. So the hypervisor is useful because it's helping strengthen isolation boundaries. Yeah.
Okay, thank you.
My understanding, correct me if I'm mistaken, Robin. My understanding is that the regions that you're looking at creating in stage 2 are typically going to be pretty large, I would assume, in order to partition off areas for entire VMs essentially. So it's pretty coarse granularity, my understanding anyway.
Yeah, I think that's it's largely an implementation specific thing, but generally speaking, I would agree with you. Yeah.
Okay, move on.
Yes, thank you.
Okay, great. So our assignment was not to, well, okay. First of all, I guess an obvious question that people might ask is, well, wait a minute. TFA is for A cores, right? So what are we doing? Why are we doing an R something with the code base for TFA? And the short summary is because these V8 AArch64 cores really are a whole lot like the V8 cores. They're not very much, when you really get down to it, they're not very much like the old R cores. They're really much more like the A cores, with some very obvious differences that we have seen and we'll see more of. So if we were to try to create a completely separate code base for some hypothetical TFR, we would basically be copying off a whole lot of TFA code and then having a parallel maintenance nightmare. So it's a whole lot easier to just leverage the existing TFA code and augment it a little bit with an additional platform. But I think probably the best reason to expand TFA to include V8-R64 support is that, well, this is open source software, and the whole point of open source software is to get as many contributions from a larger community, both contributions and reviews from a large community. And if we can get people from the V8-R64 community to join in that effort, I mean, I'm all for it. I think it's great to have more eyes on the problem. So it's a community effort, and if we have a larger community, we're better. Yes.
The other thing I just quickly add to that, Gary, is that I mean, I'm assuming the forum here is kind of familiar with the ARM architecture reference manual, right? So it's quite telling that and I'm sure Gary has a link later on, but the V8-R64 reference manual is actually relatively a very short addendum on top of the V8A architecture reference manual. And the reason it is that way is because it's fundamentally the same, barring the kind of the traditionally larger emphasis on PMSA and now the co-location PMSA. But it's fundamentally very similar.
Now, the immediate assignment that we had was not to port all of TFA. That was not really much of interest, at least immediately. The main assignment, initially at least, is simply to be able to do a secure boot of an operating system designed specifically for a particular purpose. And so to do that, all we really had to do was port BL1 and then adapt BL1 so that it would not load BL2, but instead load the runtime system, the partner's runtime system. And so that's essentially what we have done to date. So yeah, and also, of course, support firmware update and recovery mode firmware update. Oh, sorry. I guess Lauren was going to do this slide. Sorry.
I can explain that. So this is just the boot flow, kind of a block diagram of it, of what we just discussed. So we have BL1, and that's the main boot stage, boot image. And that's now we ported it to EL2. So instead of EL3, and that loads the runtime system and then does the external handoff to that. So this is just an example runtime system of a potential partner's setup. So here is Zen running in EL2 and running Zephyr and Linux in parallel in EL1. So yeah, this is just an example of how that could be.
Zen is a commonly used hypervisor for with Zephyr as an RTOS.
So quick question on that, right? Now we're jumping directly from BL1 or boot ROM to something like Zen. So usually Zen, Linux, Zephyr, these OSs and hypervisors have some boot protocol that they expect from firmware, right? Firmware is expected to have X0, X1.2, whatever, right? So now are we putting all that stuff into boot ROM, or how are we abstracting that out?
So I think we'll talk about that later. Is that true? Lauren, I think we'll be answering that sort of thing later.
Yeah, I can get more into that later.
Yeah, okay, thanks.
Is that okay? Is that okay? Mm-hmm. Okay. All right. Yeah, so as we mentioned, there's no EL3 on these cores. So what are the ramifications of that? Well, a lot of ramifications, but the actual instruction set is and the basic architecture is the same, but you don't have any EL3 system registers, right? So we have to run, and of course we have to run BL1 in EL2, which essentially becomes, well, we think of it as running BL1 in EL max, which is normally EL3, but in this case will be EL2. So we don't have any EL3 registers, so we had to redirect those accesses to the EL3 registers to the corresponding EL2 registers. And in most cases, they mapped really quite closely. I did a careful survey of all of the accesses to EL3 registers and looking at what fields they accessed and so forth. And there were only a handful where the fields were mapped differently between the EL3 register and the EL2 register, and a few minor changes to that. And to do that, we created an EL max common macros, essentially replacing the EL3 common macros.s. We will probably, as further reviews go, we'll probably find EL max .s handling some calls, some macro calls, and then partitioning them off based upon the parameter that you pass in to an EL3 common macros or an EL2 common macros. Currently, it's all architected into one EL max common macros. But anyway, if you choose to review the code, you will see EL max common macros, but we'll probably be adding back EL3 common macros and EL2 common macros distributed to from this one. Anyway, just FYI. Yeah. So MPUs, just as a review again, for any of you who have not dealt with MPUs, yeah, it's strictly flat mapped. Just so as Robin pointed out, it's strictly flat mapping of memory, and it's all about applying protections. The documentation still describes what MPUs do as translations, and that's reasonable, because from a conceptual perspective, it's still memory management when you really get down to it. But it can also, to some degree, translate attributes of the. But they still call it translations, but addresses do not change. PA and IPAVA, they're all flat map same. But most importantly, MPUs are register-based, strictly register-based. There's no table walks of tables and of page tables in memory. There's none of that. And of course, there's a limited number of registers that you can use to define regions of memory. In particular, you have these base address registers and limit address registers, which specify the base address and the end address, the limit address of a block of memory, a region. And the limit address, the PRLAR, also specifies which mayor, which is just like on a MMU translation, the mayors specify what kinds of attributes or permissions are available for that. Similarly, they point to the mayor registers. And then there's a single register bit mapping, which particular regions are enabled. So obviously you have far fewer, you have far fewer regions that you can deal with in on an MPU, but there's a slight advantage that you have finer resolution on those, because you don't have page boundaries to deal with. You don't have to limit it to 4K or anyway. Yeah, let's see. I think I got most of this slide covered. Right. So another curious ramification, again, with no EL3, you can't swap between secure and non-secure. So everything is declared secure, which arguably means that nothing is secure, or nothing is any more secure than anything else anyway. But in any case, it's important, however, to, because translations have to be defined as secure or not, that we make clear whether you're using secure thought. And that actually works out as well better, because BL1 normally is running in secure. So the translations are all marked as secure, let's put it that way. So we can basically use those translations with very little change, because they're already marked as secure. Yeah, so yeah, I just made a note here that there are options with the MPU, just as in the MMU, to generate non-secure memory transactions from secure execution, but we have not yet had any need to do that, but maybe at some point in the future it might be useful, perhaps. But we haven't needed to do that at this point. The details.
Yeah, so getting into more of the details of loading the runtime system and transfer control. So this is basically the changes to BL1 as far as loading and transferring to BL3.3. So now it's in, BL1 is now in EL2, and BL1 enables the MPU, and then it loads the BL3.3 image, which for our purposes is the customer partner runtime system, or the boot wrapped OS. And then it authenticates that BL3.3 image. I've extended the TBBR support to the Wehrmeister platform for authentication of that. And then, the BL3.3 image has been loaded, and then you turn off the MPU and clear the regions, and before taking an ERET to jump to the base address of the BL3.3 image for execution. So we make sure that the MPU is turned off and clear, so that you're starting fresh, essentially, with whatever the partner customer runtime system wants to set up. And then finally, we tested the BL3.3 image, the transfer to there, using an internal boot wrapped OS. And just looked for like the shell prompt of a UART to show a sign of life, to make sure that that process had been done correctly. You can kind of see it in the flow chart. And then also for transfer from BL1 to recovery mode firmware update, there was really no change. It remains the same as normally it would in BL1, where it copies the image from external interfaces and updates to the image if it can be authenticated.
So under the current assignment, the assumption is that we're not trying to dictate anything about the nature of the partner / customer OS. So we want to produce the illusion, to a fair degree at least, produce the illusion they're coming out of reset directly into their code. I'm oversimplifying, but to some degree we want to just not influence their code at all.
So bootstrapped essentially means there is no protocol to transfer, right? It's just a simple ERET, and everything else is in this bootstrapped OS.
Yes, so that the runtime system essentially taken care of in that boot wrapped OS, as opposed to having BL3.1 functionality in the firmware itself.
So just to kind of help with that, it might help to consider like some of the kind of boot chains that we are experimenting with, which we know our partners are interested in. A popular one is, sorry, can you hear me?
Yes, I'm sorry, go ahead. You have a good suggestion, let's hear it.
Yeah, sorry, yeah, I was just saying that the pattern that is the one that we know is gaining kind of interest is one where we have this firmware handing off to a traditional V8-A kind of bootloader, which would normally run on the non-secure side, like U-boot, right? And because of the fundamental similarities between V8-A and Wehrmeister 64, the boot protocol for U-boot to bring up the subsequent link in the boot chain, like the Linux kernel or like the Zen hypervisor, which follows the Linux boot protocol, by the way, for AArch64, is exactly that. Right? So nothing changes there. There are some subtleties around the MPU being present, but barring that, everything that is kind of documented in the Linux AArch64 boot protocol document inside the Linux kernel applies over here as well, in terms of register values, in terms of the state of the MMU insofar as Linux goes, etc., etc. So no disruption over there. And where there are changes, we will make sure we document those and socialize those. For the large part, when we tried to get this boot flow that I mentioned going, we had to make no modifications to anything. There were modifications to U-boot to deal with some of the MPU aspects. There were no modifications required to Linux. We are planning to make some cleanups over there just to make the MPU V8 R64 story for Linux and the traditional V8 R64 story kind of cohabit more easily. Yeah, so I just wanted to call that out. But insofar as the traditional boot protocol goes, nothing really is expected to change. And when there is a change, we are going to make sure we document and socialize that using the established channels. Yeah.
Right. So between the OS and bootloader, I understand, right? I guess my main question was between, BL1 and, whatever comes next, right? So today, I think in TFA, BL31 passes or could pass some parameters and registers to the normal world, right? But yeah, it sounds like BL1 to whatever comes next is a extremely simple E-rate with no parameters passed. Is
Currently,
that accurate?
That's our assignment. Yeah.
Yeah. So
Thank you.
I'm not a firmware expert, so I'll defer to Lauren and Chiari. But this kind of reminds me of in U-boot parlance, the kind of what do they call it? The SPL kind of story, as in there is some firmware and then there is some kind of partner dependent, if you like, protocol for kind of like handing off from the firmware to the next stage. It's kind of like that. Having said that, if there is evidence that we need to be more prescriptive over here, then please do provide us with that feedback, and then we can reason about it.
Yeah, absolutely. What we have been asked to do this time around is comparatively simple, but if you guys have suggestions for future enhancements to this, absolutely, we'd love to hear them.
Cool. Yeah. So, and one thing we wanted to mention too is, as far as the FVP goes for our class, there were changes in the memory map that were needed for adding this to TFA. So the main big difference is the memory map is really similar to the 8A, but the upper 2 GB and lower gigabyte are switched. This is actually the same on all R class cores, but in particular for the R64. And so we have, basically that means just that the bit 31 is reversed. So we have some links here to show the difference in the memory map there. Just something we had to take into account.
Yeah, if you're used to moving around in the debugger and has addresses that you're used to seeing, they're going to be like wrong. So yeah, in terms of how we ported stuff, we obviously had to deal with the MPU. So we created an MPU translate, and so the XLAT tables and XLAT tables v2 were already there in the live directory. We added a XLAT MPU. Again, the documentation still calls them translations, even though the addresses aren't changing. So XLAT MPU seemed reasonable name for it. The API is pretty similar. Where applicable, I mean, obviously some calls don't make any sense, obviously, but for the most part, the API is pretty similar. The enable calls changed into enable MPU instead of MU, but similarly for disables, but pretty similar. otherwise pretty similar API where applicable. And we also created a pound-defined configuration for no EL3, as we called it. We'll probably change that to EL1 at EL2, kind of analogous with EL2 at EL3, right? That existing anyway, so that we can control it more finely in the future if that's ever of interest. And
then
anyway,
we also, yeah, we created the F8-R platform. So that's where you'll find the platform specific code that uses all of the MPU and the different pound defines. So this is patterned after the R80 or Cortex R82.
so that's a plat. In other words, that's plat ARM board F8-R, I think is what.
Yeah, so parallel to the FPP platforms. And so that just, yeah, that includes the EL1 image that, yeah, as we said, stays in EL2 using the MPU, loads the BL33 image, and then wipes the MP region before jumping to the BL33 image. And yeah, for our testing purposes for that, we've been using an internal OS to test the transfer of control.
I almost forgot the XLAT MPU library that's in there now currently only addresses EL2. It's only enough for EL1 purposes currently, but perhaps in the future we'll maybe expand it to make it more general. Perhaps we'll see. And so we recently, like yesterday, upstreamed from our internal reviews into the real thing. So these are the Garrett reviews. Feel free to start looking them over, and so yeah, definitely love to hear your thoughts. And hopefully, I don't know whether I'm going to be going on vacation for July, so I may or not be able to do this, but I'm hoping I'll be able to do what I described here. So close your eyes and imagine this. Imagine a table, okay? And this table has a row for every new file that we have added to it. New files are kind of annoying whenever you introduce a new platform, because there's a whole lot of new files. And of course, obviously, Garrett has no idea that you actually modified to create this new file. You actually took an old file and tweaked it appropriately, but Garrett has no idea of that. So in order to make the reviews easier, what I'm hoping to do is, again, create a table that has a row for each new file, and give you information about which of the Garrett reviews created it and which ones then subsequently modified it. And more importantly, click on a link that will pop up an SDiff output showing a comparison between the new file and its closest pre-existing equivalent, so that you can see what we changed from a pre-existing file that you've probably already seen, rather than just what Garrett shows you, which is, well, there was nothing before and now there's something, which doesn't give you a whole lot to go on. So if I have time before I go on vacation, I'll create this this Fabricator site. But if not, I'll try to do it after I get back from vacation. But anyway. But we did that sort of thing for internal reviews, and I think it was helpful. But yeah, some resources here. We'll be posting the slides, of course, in the usual Tech Forum site, and these links should be live. It'll take you to view these. This perhaps this, if I remember right, this one is perhaps the most interesting in terms of understanding the Wehrmeister architecture, but the actual new processor, the RD2, this has some good overview information in there. But yes, hopefully you can get some good information, some good background from there. I think that's my slide. Yes. All right. How many languages do we know? Right. I know a few of these.
So there's just there's a couple of things I wanted to add. Firstly, thanks, Lauren and Gary. This is super useful um, for me as well. I just had a couple of things to add on top of that. One is just putting a little bit more kind of meat on the use cases, right? So you mentioned computation storage and automotive, and just for this forum's benefit, basically any kind of use case where people were kind of traditionally looking to use like a companion core with the deterministic core, where the companion core was doing things that don't fit the kind of time determinism sensitivity spectrum, right, with the deterministic core. A lot of those use cases are now kind of possible to the hardware it's possible to consolidate the hardware now. So that's driving a lot of interest with this, right? So, oh, now I can run a rich operating system along with my classic AutoSAR or whatever, RTOS.
I'm not sure whether, just real quickly, I'm not sure whether this applies in the cases, in the scenarios that we're looking at, but I know back when I was working several years ago, when I was working at Freescale in the automotive area, the customer, the automotive people that we were working with were very concerned with the total number of ECUs, total number of electronic control units that they were spending a lot of cost in installing and wiring up all of these ECUs. So one thing they wanted to do was to take an ECU that currently does engine control and integrate onto it some additional functions that are less real-time intensive, like, for instance, displays on the dashboard related to the engine, and have those operate within the same ECU so that they don't have to wire up two ECUs when they could wire in just a single one that would do those same functions. I don't know whether that's a case in the types of applications we're talking about, but that's, I know, a case that I was looking at when I was still in the automotive arena.
Yes, I think fundamentally, yes. Of course, the OEMs who try and do this kind of consolidation do a lot of diligent evaluation to understand what the tipping point is in terms of the trade-off between saving cash by doing consolidation versus pronouncing the safety rationalization problems, right? So, but they know how to do that. But fundamentally, yes, consolidation is seen as a big win. The other thing I wanted to call out is you'll start seeing Wehrmeister AArch64 implementations being spoken of in the context of in quotes edge applications and any application where you have data available on the remote side, for example, and you would rely on squirting that data to some server in the cloud or whatever for processing. There are a lot of applications where people want to try and now do at least the pre-processing of that data at the edge itself, and that's another area where the AArch64 implementations are getting a really good kind of grounding over there. One final thing I wanted to say was, so just taking the computation storage use case, right? So what people want to do there is let an RTOS run the algorithms that do disk drive, head positioning and all of that kind of stuff. But always kind of timestamp access times and things like that and keep them in some buffer. And then have a rich operating system like Linux, usually during downtimes of the RTOS, kind of process this data using some pre-trained neural networks to look for some kind of optimization potential in terms of how the data is laid out, considering wear leveling and all the other things. Okay, so that's kind of an example. I just wanted to also call out that yes, this doesn't have a secure and non-secure split, this particular architecture and implementation. And there's a reason why. One is the fact that you kind of it's an evolution of the previous generation, and even in the previous generation, the the fundamental idea was that, you know, implementations of these architectures would be in systems where there was already a secure and non-secure partition at the system level. And this particular processing element would rely inside the secure partition. So that makes sense. Furthermore, because this is the kind of automotive domain that's being targeted for a large part, the kind of cost of rationalizing software for safety is prohibitive in any case. And the feeling was that by throwing security into the mix, that complicates things. I don't agree with that rationale completely, but that's an interesting kind of data point that was shared with me. Gary and Lauren have already mentioned that the architecture allows kind of manipulation and of non-secure and secure address spaces, despite all of the exception levels being only secure. And that fits well with trying to implement a secure and non-secure kind of root of trust design using something similar to FFA, but for the V8-R universe. So we're currently exploring that. What I mean is like a platform security architecture story for the V8-R64 architecture. But we haven't mentioned that here because it wasn't really relevant at this stage. But if anyone wants to talk about that, please do reach out. That's all I had to say.
Yeah, we're definitely interested in hearing any ideas you folks have about how we can do more in this regard. If you have any ideas, we'd definitely love to hear them. Any other questions? Right. Well, cool. I will go ahead and stop the recording. All right, everything's off.